On August 10, 2026, one of the most consequential rocket failures in recent history unfolded over 85 seconds. A Long March 7A rocket carrying China's ChinaSat 4B satellite tore itself apart in the morning sky above Hainan province. It was a catastrophic, violent, very public failure. But this isn't just a story about one rocket, one satellite, or even one mission. What happened on that August morning exposes deep vulnerabilities in China's space ambitions, vulnerabilities that will reshape the entire space race for the next decade. And it raises critical questions about how quickly any nation can expand into space without sacrificing the quality and reliability that truly advanced spaceflight demands. Today we're doing a deep dive into what went wrong, why it matters geopolitically, and what comes next. Let's start with the facts. August 10, 2026. Wenchang Space Launch Site in Hainan Province, China. The Long March 7A rocket sat on the pad, fueled, checked, approved. This is one of China's workhorse rockets, not their most powerful, but reliable enough to be assigned to critical missions. The payload, ChinaSat 4B, a geostationary communications satellite worth somewhere between 150 to 200 million. Not a fortune by space standards, but a significant asset. Liftoff occurred at the scheduled time. The first stage engines ignited. For the first 85 seconds, everything appeared nominal. The rocket climbed through the lower atmosphere, accelerating, building altitude. The vehicle was operating as designed, or so the telemetry suggested. Engineers in mission control were monitoring. Everything looked good. Then, at T+85 seconds, during the most dynamic phase of flight, the period of maximum aerodynamic pressure, when the rocket is traveling fastest through the densest part of the atmosphere, something catastrophic happened. The telemetry stream stopped. Ground tracking stations lost contact, and within moments, eyewitnesses reported seeing a massive fireball in the sky. The rocket had torn itself apart. The explosion was visible for miles. Debris fell across the launch site and surrounding areas. The satellite was destroyed. The rocket was destroyed. And something far more important was now in question. Why? This wasn't a small anomaly. This wasn't a minor glitch. This was a structural failure catastrophic enough to destroy the entire vehicle. And in the world of spaceflight, when something like this happens, it doesn't just affect that one rocket. It affects everything built like that rocket. Here's what makes this failure a geopolitical earthquake, not just a technical accident. The Long March 7A uses the YF-100 engine. This is a liquid-fueled rocket engine that represents the cutting edge of China's propulsion technology. It's powerful, it's sophisticated, it's relatively new, and it's the foundation of China's entire modern rocket architecture. Think about it this way. When you design a new rocket family, you typically design a core engine that will power multiple variants. China did this with the YF-100. The YF-100 powers the first stage of the Long March 7A. The YF-100 powers the boosters of the Long March 5, China's heavy-lift rocket. The YF-100 is slated to power future variants being developed. It's not an exaggeration to say that the YF-100 is the backbone of China's next-generation spaceflight capability. So when a Long March 7A using YF-100 engines exploded on August 10th, the immediate response from Chinese space authorities was to ground the entire fleet, not just the Long March 7A, but also the Long March 5 because it uses the same YF-100 boosters. Any rocket with YF-100 engines went under investigation. Now, why is this a problem? Because the Long March 5 is the rocket China is planning to use for their most ambitious missions. The Chang'e 7 lunar mission, future deep space missions, crewed missions to space stations. The Long March 5 is literally the cornerstone of China's human spaceflight and deep space exploration program. The investigation process is rigorous and time-consuming. Engineers have to pull telemetry data from the Long March 7A launch. They have to analyze propulsion pressure logs, the detailed records of combustion chamber pressure, nozzle temperature, thrust profile, everything the engines experienced during flight. They have to cross-reference that with optical tracking data captured by ground stations. They have to examine any debris recovered from the launch site. They have to run computer simulations of what stress patterns would have existed during that 85-second flight profile. And they have to do this to figure out, was there a material defect in the YF-100 engines themselves? Was there a manufacturing flaw in how the engines were assembled? Was there a design weakness that only manifests under specific conditions? Certain combustion chamber pressures, certain thrust profiles, certain acceleration rates? Was it a maintenance issue? An issue with how the engines were stored or transported before launch? The list of possibilities is long, and each one requires different levels of investigation and different levels of remediation. We're talking about combustion instability, a phenomenon where the flames inside the combustion chamber start oscillating in ways that damage engine structure. We're talking about material fatigue, where repeated cycles of heating and cooling gradually weaken metal structures. We're talking about thermal stress, where different parts of the engine expand and contract at different rates under extreme heat, causing cracks. We're talking about bearing failures, seal failures, turbopump problems. These aren't theoretical problems. They're issues that have plagued every rocket program in history. The fact that they appear to be afflicting China's YF-100 engine program at scale, and at scale is the operative phrase here, tells us something important about the state of Chinese aerospace engineering. Here's the context that makes this failure especially significant. August 10th wasn't an anomaly. It was part of a pattern. China launched 56 times in 2026 before the Long March 7A failure. 56 orbital launches. That's an astonishing cadence. It's more than any other nation. The United States launched fewer than 40 times in the same period. Russia and Europe combined launched significantly less. By sheer numbers, China is winning the launch rate game. But embedded in those 56 launches are failures. In January 2026, the Long March 3B experienced a failure. In January, the Series 2 solid rocket had a failure on its debut flight. In April 2026, the Tianlong 3 rocket, another new vehicle from a commercial provider, failed on its maiden flight. And now, in August, the Long March 7A. 4 failures, 8 months, 56 launches. The failure rate is approximately 7%. For context, that's not catastrophic by historical standards. The Soviet Union had failure rates like that during their early programs. But it's higher than modern American vehicles. SpaceX achieved something like a 95% success rate with Falcon 9. Blue Origin's New Shepard and New Glenn are targeting similar reliability levels. The Long March family historically operated at higher reliability levels than 93%. So something has changed in China's space program. And the most likely explanation is that they've expanded too quickly. Think about what China's space sector has been doing. They've been increasing the number of launches year over year. They've brought commercial companies into the market alongside state entities, creating competition but also fragmentation. They've introduced new rocket families faster than they're testing them. They've tried to maintain a rapid cadence while simultaneously innovating and developing cutting-edge technologies like the YF-100. This is classic engineering tension. Speed and innovation are in constant conflict. You can build things fast, or you can build things right. Building them both fast and right requires extraordinary discipline and investment. And it appears that China may have prioritized speed without sufficient parallel investment in quality assurance and testing. The Long March 3B failure, the Series 2 failure, the Tianlong 3 failure, these were all different rockets, different companies, different technologies. The common thread was they were all part of aggressive expansion. And now the Long March 7A, a rocket that was supposed to be reliable and proven, experienced a catastrophic failure. But here's where this gets from technical problem to geopolitical crisis. The Long March 5 that's grounded? It was supposed to launch China's Chang'e 7 mission in August 2026. That's now. That's weeks away. Or it was weeks away. Now it's uncertain. Let me explain what Chang'e 7 is, because this mission embodies everything China's trying to accomplish in space right now. Chang'e 7 is the 7th mission in China's lunar exploration program. It consists of 4 separate spacecraft: an orbiter, a lander, a small hopping rover, and a mini probe. The mission is targeted at the lunar South Pole region, specifically the Aitken Basin area. This is the same region the United States has been studying intensively with orbital reconnaissance. It's the same region international space agencies consider strategically vital for future human lunar bases. Why the South Pole? Because of one substance: water ice. The lunar South Pole is cold enough that water ice can accumulate in permanently shadowed regions. Water ice is valuable because it can be mined and processed, turned into drinking water for astronauts, or broken down into hydrogen and oxygen for rocket fuel. A base at the South Pole with access to water ice would be self-sustaining in ways that other lunar locations cannot be. Chang'e 7 is specifically designed to land in these permanently shadowed regions, deploy a rover and a hopping probe to map ice deposits, and gather data that will inform where future bases should be located. It's not a crewed mission. It's a scout mission. But it's a crucial scout mission, because it's gathering information that will determine whether humans will be able to establish a sustained presence at the lunar South Pole. China has been very public about its ambitions to establish a lunar base in the next 10-15 years. Chang'e 7 is a key milestone on that path. The mission schedule is built into China's entire deep space exploration roadmap. Chang'e 8 is planned for 2027 or 2028. Chang'e 9 and 10 are planned for the early 2030s. These missions are designed to work together, to gather different types of data, to progressively build toward a sustained presence. So when the Long March 5 that was supposed to launch Chang'e 7 goes under investigation, the entire timeline gets compressed. The question isn't just, will Chang'e 7 launch? The question is, when will Chang'e 7 launch? And the follow-up question is, what does that mean for Chang'e 8, 9, and 10? If Chang'e 7 slips from August to September, that's 4 weeks of delay. That might not sound like much, but in the space business, every month matters. Launch windows are determined by the relative positions of Earth and Moon. Miss a window, and you might have to wait weeks or months for the next opportunity. The lunar South Pole is particularly constrained. There are only specific times of year when the illumination conditions and orbital mechanics align for a South Pole mission. So if Chang'e 7 can't launch in August, the next available window might be in October or November, or it might be in 2027. And if Chang'e 7 slips to 2027, then Chang'e 8 gets compressed. And then Chang'e 9 and 10 get compressed. The entire sequence of Chinese deep space exploration missions gets disrupted. That's bad for China's timeline. But it's also significant for everyone else in the space race. The space race isn't just about China and the United States anymore. The space race has become multipolar. The United States has NASA's Artemis program, which is targeting a return of humans to the moon by the late 2020s. Artemis 2 is scheduled for the mid-2020s, now approaching. Artemis 3, which will land humans on the moon, is planned for the late 2020s. The US is in a relatively steady state with Artemis. There have been delays, yes, but the program is advancing methodically. India has the Chandrayaan program. India successfully landed on the lunar South Pole with Chandrayaan 3 in 2023. India demonstrated that they could reach the most strategically important region of the moon. India is now planning Chandrayaan 4 and Chandrayaan 5. India has momentum and demonstrated capability. Japan has the Slim Moon Lander program, Europe has lunar aspirations and Artemis partnership commitments. Even private companies are getting involved. Companies like Axiom Space and other commercial lunar lander companies are developing vehicles. Against this backdrop, China's lunar program is trying to move faster, achieve more, and establish a credible alternative pathway to space exploration. Chang'e 7 was supposed to demonstrate that China has the technical capability to operate complex missions at the lunar South Pole. It was supposed to show that China could land in the most strategically important location and operate there reliably. Now, Chang'e 7's timeline is uncertain, and that's an opening for other nations. If the US manages to land humans on the moon through Artemis 3 before China has demonstrated sustained operations at the South Pole, that changes the narrative. It changes the power dynamic. It suggests that the US is still the more capable space power, not China. For China's space planners, this isn't just about one mission. It's about positioning China as the next great space power. It's about showing that they can accomplish what the US accomplished 50 years ago, but do it in ways that are uniquely Chinese. It's about soft power and technological prestige, and the geopolitical messaging that comes with being a spacefaring nation. A delay to Chang'e 7 erodes that messaging. It suggests that China's space program has vulnerabilities. It suggests that rapid expansion has costs. It suggests that, despite China's impressive launch numbers, they still have to deal with the same engineering challenges that every space program faces. There's also a military dimension to consider. The loss of ChinaSat 4B is a military-relevant loss, even if the satellite itself wasn't explicitly military. Geostationary communications satellites are dual-use infrastructure. They carry civilian communications, but they also carry military communications. They provide strategic command and control capabilities. They support military operations across regions where China has interests. The Chinese military is increasingly reliant on space-based communications and surveillance. The loss of a communications satellite, combined with the grounding of the Long March 5, which is China's most powerful rocket, creates temporary vulnerability in Chinese military space capabilities. During the investigation period, China's ability to launch new military satellites or replenish existing constellations is constrained. That's a window of opportunity for other nations. It's a window where the US, if it wanted to, could accelerate certain space-based military capabilities. It's a window where other nations competing with China can make relative progress. Now let's talk about what this failure tells us about the state of Chinese aerospace engineering at a deeper level. The YF-100 engine represents China's attempt to design and manufacture an advanced rocket engine that matches or exceeds the capabilities of engines developed by the United States and Russia. The Russian RD-180 engine, used on American rockets, ironically, has been in service since the 1980s. It's battle-tested. The American RS-25 has decades of flight history. The RL-10, another American engine, has been in service since the 1960s and flew hundreds of times. The YF-100 is relatively new. It represents cutting-edge Chinese technology, and it represents an attempt by China to develop entirely domestically what the US and Russia have taken decades to perfect. There's nothing wrong with that ambition. Every nation that wants to be a spacefaring power has to develop these capabilities. But there's an engineering truth here. Developing advanced rocket engines is hard. It's hard because you're dealing with materials at extreme temperatures, extreme pressures, extreme stress conditions. Combustion chamber temperatures can exceed 3000 Kelvin. Pressures can reach 300 atmospheres. Vibration and acoustic loads can be enormous. And all of these stresses are happening simultaneously for short bursts, with zero margin for error. The US and Russia developed their engines over decades, with hundreds of test firings, refinements, iterative improvements. They had funding. They had expert teams. They had the time to get it right. China has compressed that development timeline. The YF-100 went from design to operational use faster than historical precedent would suggest. And now it's failing. Is this a design problem? Is it a manufacturing problem? Is it a quality control problem? We don't know yet. But the pattern of failures across different rocket families in 2026 suggests that there's systemic stress in China's space industrial base. There's pressure to produce, to meet timelines, to demonstrate capability. And under that pressure, quality control may have been compromised. This is a cautionary tale that applies beyond China. It applies to every nation and every company trying to expand spaceflight operations rapidly. SpaceX initially had failures. Blue Origin has had setbacks. Every spacefaring entity has faced this trade-off: speed versus reliability. And the ones that succeeded are the ones that ultimately prioritized reliability, even when it meant accepting delays. For China, the question now is whether they'll make the same prioritization. Will they slow down their launch cadence to improve quality control? Or will they push forward and accept a higher failure rate? The YF-100 investigation is now underway. Chinese space agencies have established an anomaly investigation board. Engineers are analyzing every piece of available data. They're examining the rocket debris that was recovered. They're running simulations. They're analyzing the telemetry stream up to the moment of failure. The investigation will likely take weeks. The goal is to identify the root cause of the failure. Is it something that could have been caught through better testing? Is it something that requires a design change? Is it something that requires a manufacturing process modification? Is it something that requires a materials change? Once the root cause is identified, the fix has to be implemented. If it's a design change, that means engineering work, analysis, potentially new test firings. If it's a manufacturing process change, that means identifying which engines might be affected, potentially inspecting the existing fleet, potentially recertifying engines. If it's a materials change, that means qualifying new materials, testing them, ensuring they work at scale. Then comes recertification. Before the Long March 5 can resume flight with a crewed mission like Chang'e 7, or before the Long March 7A can resume commercial operations, the YF-100 fleet has to be certified as safe. That might involve additional test firings. It might involve analysis of the current engine fleet to ensure no other engines are affected. It might involve inspections of all engines in inventory. This process typically takes 4 to 8 weeks minimum. It could stretch to 12 weeks if the root cause is complex. During this entire window, the Long March 5 and 7A are grounded. What happens to Chinese launches during this period? They shift to other rockets. China still operates the Long March 2, 3, and 4 variants. These are older rockets that use proven engines. They're not as powerful as the 5 and 7A, but they can lift many payloads. So we can expect a shift in the Chinese launch manifest. Smaller satellites go on Long March 2, 3, and 4. Larger satellites either wait or go on commercial launches from other countries. But there's only so much capacity on the older rockets. And China has been aggressive about launching satellites. The backlog of satellites waiting to launch will grow. Some commercial customers might have to find alternative launch providers, which means paying more, which means higher costs, which means lower revenue for Chinese launch services. The strategic impact is clear. China's space program has been disrupted. Not catastrophically, not permanently, but disrupted. Let's zoom out and think about what this means for the US-China competition in space more broadly. For years, the narrative in Washington has been that China is a rising space power that might eventually match or exceed the US. The evidence for this comes from China's launch rate, their lunar program, their ambitions for crewed spaceflight, their plans for space stations, their satellite constellations. By a lot of metrics, China is impressive. But this failure is a data point that complicates that narrative. It suggests that rapid expansion, while impressive in aggregate numbers, has costs in terms of reliability and engineering maturity. The US space sector, particularly companies like SpaceX, has achieved high reliability through decades of focus on quality, testing, and iterative improvement. SpaceX's Falcon 9 rocket has become incredibly reliable. The company achieved dozens of consecutive successful launches at one point. Blue Origin's New Shepard has demonstrated reliability on suborbital flights. The US has the advantage of decades of spaceflight experience, accumulated expertise, and engineering culture that prioritizes reliability. China is trying to compress that timeline. They're trying to achieve in 10-15 years what the US achieved over 60 years. It's an ambitious goal, but this failure suggests that compressing the timeline has consequences. For the US government, this is a modest, strategic win. It suggests that American space capabilities maintain an edge. It suggests that the competition, while real and serious, isn't as one-sided as some have feared. But the US shouldn't be complacent. China will learn from this failure. They'll invest more in quality control. They'll fix the YF-100 engine. They'll return to their ambitious launch cadence. The failure is a temporary setback, not a permanent limitation. There's also the question of whether other nations will learn from this. India, Japan, Europe. They're all watching China's failure and drawing their own conclusions about what it takes to operate reliably in space. At a deeper level, this failure tells us something about how space programs need to be organized and managed. The Chinese space program is a hybrid. It has state entities, military involvement, and increasingly, commercial companies. This creates complexity. Different organizations have different priorities, different timelines, different pressure points. State entities might prioritize political optics and schedule adherence. Military users might prioritize capability and redundancy. Commercial companies might prioritize cost and revenue. Managing these different incentives is hard, and it's possible that the aggressive launch schedule reflected pressure from multiple parts of the Chinese space ecosystem pushing for results at different speeds. By contrast, the US space program, particularly after the NASA SpaceX partnership model emerged, has been relatively unified in prioritizing reliability. SpaceX's entire business model depends on reliable rockets. If SpaceX has failures, it loses customers and revenue. That creates powerful incentives for quality. NASA spacecraft are thoroughly tested and retested. Private companies like Blue Origin are building long-term businesses that depend on reliability. This model, where reliability is built into the incentive structure, not just an aspiration, has proven effective. China's space program might benefit from examining whether its organizational structure and incentive systems are optimized for reliability as much as for throughput. It's a difficult question for Chinese space planners to grapple with, because improving reliability typically means slower launches, not faster ones. It means investing more in testing, more in quality assurance, more in engineer time and attention per mission. But in the long run, reliability is what builds credibility as a spacefaring nation. So what happens next? Where does the space race go from here? In the short term, we're in a waiting period. The investigation unfolds. The YF-100 fleet is analyzed. Engineers work to identify the root cause. Assuming no other surprises, we can expect the Long March 5 and 7A to resume operations within 6 to 8 weeks. Chang'e 7, assuming no other delays, might launch in October or November 2026 rather than August. That's a meaningful delay from China's perspective, but not catastrophic. The moon mission can still happen. It's just pushed back a few months. But those few months matter, because other nations are also pursuing lunar missions with their own timelines. Artemis 3, if it stays on schedule, might launch humans to the moon within a year or two. Every month that China's timeline slips is a month where the US potentially pulls ahead. Every month matters in the space race because the stakes are high. Whoever demonstrates sustained capability at the lunar South Pole first gains strategic advantage. In the medium term, the question is whether China's space program learns the right lessons. Do they invest more in quality control? Do they slow their launch cadence to prioritize reliability? Do they restructure their space industrial base to reduce pressure on individual providers? Or do they push forward with business as usual, accepting higher failure rates as a cost of rapid expansion? The answer to these questions will determine whether China eventually becomes a truly mature spacefaring power or remains a rising power with impressive throughput but concerning reliability. In the long term, the space race is evolving beyond just national governments. Commercial companies, private space stations, space tourism, asteroid mining, the space industry is becoming increasingly complex. Nations like China that can master both government space missions and commercial space activities will have advantages. Nations that can't will find themselves increasingly dependent on foreign launch providers, which creates vulnerabilities. For China, developing a reliable space industry, both government and commercial, is essential to their broader strategy of technological independence and great power status. This failure is a reminder that despite rapid progress, they're not quite there yet. So let's bring this back to the opening question. Why does a rocket explosion on August 10, 2026 matter? It matters because it exposes the trade-offs inherent in rapid expansion in any complex technical field. It matters because space is increasingly a domain where geopolitical competition plays out. It matters because the next decade of human space exploration, who reaches the moon, who establishes bases, who proves capability, will be shaped by decisions made by space agencies and their industrial partners today. For China, this is a moment of reckoning. It's a moment to ask, what kind of space program do we want to be? Do we want to be the nation with the most launches? Or do we want to be the nation with the most reliable launches? Do we want speed or sustainability? Can we have both? For the United States, this is a moment of validation, but also caution. Validation that American space capabilities, particularly commercial spaceflight, have achieved real advantages in reliability and maturity. Caution because China is large, has resources, has talent, and has demonstrated ability to learn from failures and improve. For the rest of the world, India, Japan, Europe, commercial companies, spacefaring nations, this is a lesson in what it takes to operate reliably in space. It's a reminder that the space industry is not easy, that shortcuts have costs, and that sustainable spaceflight requires patience, investment, and a culture of quality. What happened on August 10, 2026 will be studied in engineering schools and space agencies for years. It will inform decisions about how to manage rapid growth in spaceflight operations. It will be a data point in the ongoing assessment of which nations are truly capable of leading the space race. And most importantly, it will shape the decisions that determine whether humanity returns to the moon sustainably, whether we eventually establish bases there, and whether space becomes a domain where multiple nations and companies operate reliably, or remains something only the most careful and deliberate powers can master. The space race continues, and this explosion, dramatic as it was, is just one chapter in a much longer story.